day to you. This is Anagalactic on the 20th day of January, and over here you'll see the circle we created, which you may recall, and don't worry if you didn't see the prior video. It was mostly to create this circle, which I'll quickly define. A circle requires very little comment as to its shape. It is a perfect shape, but this is a special circle because of its dimensionality, which we contrived. The unit circle is a contrivance which is very useful. The unit circle, in a sense, you could say is worshipped, although that's in a mathematical context of worshipping something that is so perfect that it deserves worship. Does it? Yes, in a superpositional sense. But this is not a unit circle. What is it then if it's not a unit circle? You can't see the radius. But I'll just tell you what we constructed before, whereby you would appreciate what this circle represents. The unit circle represents the number 1. Where is it? Well, I think you know. It's the radius, which could be oriented anywhere on the circle because the radius is the same all the way around the circle. That is, from the center, you dial on the x-axis to get to 1. That's the unit circle. Because all you have to do now is use the compass function and draw a circle, which this beautiful program, which is free and open source, will allow you to do with just a few quick clicks. You can set the radius to whatever you like. So this is a good geometry tool, and what are we attempting to accomplish? We're setting up a scenario for the collapse of the wave function, which can be done quite easily in circular space, although to relieve the paradox will take just a little bit more than just a reconstruction in circular space. Why do I use the phrase circular space, actually term? Is there such a thing? Well, in essence, you're looking at it because do you see any straight lines there? I don't. Oh yes, I forgot. There are 2 straight lines through the circle. Now you can see, if you could see the grid marks, that there are actually several straight lines, but they're not exactly the same kinds of straight lines in terms of the circle, because there are 2 unique straight lines in the circle. Because when you draw a diameter, you can draw another one, but they are exactly equivalent, aren't they? Because of course the radius can be dialed. Well, then you simply are like dialing on a bicycle spoke wheel. When you turn the wheel, the radius goes all the way around, and you could say make it go around 1 time, and that would be 1 on the circumference. Well, you could also do the same thing for the diameter, except now, since it's a different distance that you're twirling, it will describe what? There's a relationship, of course, between the radius and the diameter, which is a factor of 2, and that's called the diameter, which in proportion to the circumference is pi, which means that the proportion of the radius to the circumference is 2 pi. And that has been proved. We use that all the time. 2 pi is a magic irrational constant, which is also worshipped, but actually it's kind of hated. The Greeks hated it, and we've hated it ever since. And we hate 2 pi so much, we put it into every single equation that we write. In upper level physics, there is no such thing as an equation without 2 pi being written right into it. So it's a very, very important constant. And again, it's simply the constant of relationship between a circle, which you see, and its radius. And however big you draw that circle, whatever is the value of the circumference, the radius will comply with that equation on an irrational, not rational, an irrational relationship. We accept that, but you can see that there is a footnote. So the unit 1 is extremely magical. The unit 1, the smallest counting number, the beginning of the counting numbers, there is no 0 in the counting number system. It begins at 1 and it goes up in the positive direction. So there are no negative numbers in the counting number system. Why am I saying this? Because the number 1 is the smallest counting number. That is certainly not all we might say about the number 1, which you could say is a somewhat transcendental number, rivaled only by one other kind of number, and that's the number 0, which you see affixed to the Cartesian grid, which is at the center of 2 lines. And these are 2 unique lines with respect to each other in the plane. So what is the plane? The plane is very interesting to try to define, but today in the 21st century, due to an incredible amount of research done through the 20th century, we have discovered a lot about physiology, which is not my field. But I did research in a certain direction and was able to satisfy my curiosity on what I thought might be the case, and indeed is the case. What does physiology say about how we see? Particularly in my case, I was curious to validate or invalidate a hypothesis which I thought I could prove, and I was looking for secondary proof because this is somewhat interesting. How do we see? What do we see? Would you, given a multiple choice question, be able to answer the following question of how we see? Do we see lines? Do we see circles? Do we see a plane? Can we say that that's a real object, at least in our mind? I think anybody would say we can see a plane in our mind. We're actually doing so now with this diagram. We're imagining that we're seeing a planar space. And what is the characteristic of planar space that would differentiate it from, and that's actually the right word mathematically, the plane is a differentiation of volume space. That is, it lowers the dimension, we say, of volume space. So this is a flattened space. With respect to what? With respect to the way we know space actually is. We can see depth. So we know that space could be conceived as 3D. We certainly have done so. Is that natural? I thought that I could prove that it is, which was a surprise to me, because I was attempting to prove that we can see in another way. And we'll get to that in a moment, because you're going to do that too, because you can, and you should. And when you do, it'll be probably at the moment that you understand the collapse of the wave function. So I'm just giving you a clue as to what's ahead. We are studying the collapse of the wave function from a peculiar and unique point of view which nobody shares much anywhere any longer, which is that we as scientists, you and I for here and now, really insist that we're sick the fuck to death of theories. We've just grown sick of it. Einstein grew sick of it. You might say that he died of it. but I think he died of natural causes. But when he died, he was one of the most frustrated human beings that's ever lived. He did not, explicitly did not, achieve his life goal. Part of his journey, that is Albert of Switzerland, who later came to the United States, he ended up at Princeton, where I believe is where he died, with his good friend Kurt Gödel, who did die of his mathematics, almost certainly, unless he had a predisposing condition, but he lost his mind very much nearly completely, and Einstein was his bosom companion, because even crazy people have some point of reference. Be that as it may, Albert was trying to understand what he himself helped to discover, which is now called the quantum anything. And nobody knows what is meant by quantum when you go to try to define it. And we want to follow in the footsteps of one of Albert Einstein's contemporaries, an Englishman who has French extraction instead of Swiss, a man whom we all know as Paul-Édouard Maurice Dirac, who spoke both French and English, which is quite a story of his life. He's been called the strangest man. That is a title of a book by a very good author on this subject, I would say. Fermelo, Fermelo. You can get this book, I believe, for free online. That would be the only way I could explain why I was able to read it, because I did not buy it. I don't usually buy books. Because if you look hard enough, you'll usually be able to download it as a PDF. Now, this circle is not a unit circle. I'm just leaving off that story because I don't want to delay any further with my stories, my famous, endless stories. The collapse of the wave function is well in hand now, beginning right where we're at, which let me just explain to you where we're at. That is not a unit circle. It's a very special circle. It looks just like a unit circle, and with a reparameterization of some kind, it might be. But if you look at the hatch marks, the radius of that circle is less than 1. It's a very specific number which we were able to compute using the most famous equation, basically going back to the Greeks, that c equals 2 pi r. The numeric irrational constant of correlation between r and c, which I think you can guess is the radius and the circumference. The radius is always less than the circumference, but by how much? What's the relationship of proportion, if it can be found, between any radius and the circumference of that radius? When you set the radius to 1, a magic number, you are able to compute, as far as you dare to go, the circumference of that circle, which is well known now as the value pi. And it's a value, but it's not a quantity. Just accept that for now. We're just setting up the nomenclatural basis so we can be specific as we explore the collapse of the wave function, so we can see it. And once we see it, perhaps we can get the geometry, and if we do, we can get the mathematics of that geometry. Alas, I have been able to prove some very bad news. There is no way to do that anybody has ever seen. And that, I say, is the problem. Can that be solved? Yes. And nobody's ever seen the solution. It's a direct mathematics solution, translating essentially between the geometry and the mathematical system. Well, what broke? I thought that our geometry, which you can see on this screen, matches the mathematics. Not quite. No, there's no way that could possibly be absolutely true. They're two completely different spaces. This line is a space. That's a very abstract use of the word space, but it's very well accepted. A space is a place where you can put numbers, and the line is the perfect place for numbers. And in fact, my teacher, who died of the COVID virus in 2020, a man named John Horton Conway, whose name you may have heard, and if you're old enough, you may have heard his name from some of his most fascinating discoveries in playtime mathematics, of which he was not proud at all because he thought he deserved a lot more credit in his more serious, non-playful direction. And yet, what actually happened with John is one of the most ironic and yet exciting mix-ups that I've ever heard of in the strange history of science. Because John Horton Conway proved for the first time in history the definition of what is a linear number. And when he did so, he solved all the problems that Cantor was trying to solve, and many other men were trying to solve as well, which is the recontinuization of the quantized line, which is a direct contradiction. And that's perhaps why Cantor died insane, as did Gödel. So mathematics has some hazards to it attached, perhaps. Nobody's been able to prove if either Gödel or Cantor went mad because they were at the edge of mathematics. And they lost their fucking minds because they were too much involved with trying to solve a contradiction. Well, those kinds of things have persisted throughout the history of mathematics, and indeed physics, and quantum mechanics has inherited some fatal problems. And they'll never be solved unless, well, that's why I'm here. I actually saw something that everybody missed. So it's quite simple, and you're going to see it too. And it begins with this simple circle, which has a magic radius that is not 1, but it's the inverse of 2 pi. So if you use the inverse of 2 pi, which is what this radius is, which is about 0.16, and I showed you that is actually the value at C. We do have a pointer. I hope you can see that pointer. That is C right there, which is at the end of the x-axis, originating at the origin, of course, going in the positive direction on the x-axis, the most conventional and convenient place to set up the parameterization of the circle using the radius alone. Only one number is needed, as long as you have the right relationship, which is in this case, as always, a formula, also called an equation. The equation means that it's equating two quantities, in this case the radius and the circumference, but to do so, you would have to establish the constant of proportionality so that by rather simple multiplication, you can get the circumference from the radius, and of course with multiplication, that can be inverted, and you can get the radius for the circumference. Using that rather convenient inversion, it maintains the symmetry of the proportion. It maintains the symmetry on the inversion. And what's that inversion? The radius is smaller than the circumference. So the constant of conversion would be 2 pi, whereby you simply multiply the radius by that constant to get the circumference. I don't see how it can be simpler. So that's what you do, and the constant of conversion for that proportion is a fixed number, although it's not a quantity. It could be called a number. It has been called a number. It is the number pi. Now the pi refers to the diameter, so the radius would refer to 2 pi because it's a simple multiplicative relationship. So when you use that number, which could have a reduced value, 2 pi has the constant 2 in it because it refers to a radius. So I believe I'm slightly dyslexic, so if I said that backwards, I'm sure you can get it right. Let me say that again. When the radius is 1, the circumference has to be larger, so you multiply by the constant. Okay, what if you knew already by a measurement that the circumference, you measured it and it seemed to be pi? You would never be able to get that exact measurement because it's not a quantity. It can't be measured. But you can guess how close it is. And if you guess 3.14, you're very close. Certainly within a hundredth, if 3.14 is indeed correct to that decimal place, then you can plug that in and use division instead of multiplication. Because instead of starting with a radius, whereby you would need to multiply up to get a bigger number, here you have the bigger number and you're dividing by the same constant of proportion to get the radius. We capitalized on that unique relationship, because it is constant, to put the inverse of 2 pi on the radius. And that's 0.16, which is essentially 1 over 2 pi. So if you were to carry out that long division operation, which you would never be able to complete because pi is incomputable, that's technically correct. Pi is incomputable. And that's almost been proved. We do know that it's transcendental. Nobody is quite sure, because of Kurt Gödel's incompleteness theorem, whether that might someday be proved to be a number. But so far we've proved pretty much by exhaustion that pi is not a number. But that would depend on how you define number. Well, John Horton Conway put pi right in there and found out that it certainly is on the line. So pi is a linear number, at least. If it could be a number at all, it's on the line with all the other numbers, which is an amazing discovery. Because by using really transinduction, it goes by a different name, transrecursion or transreduction. It's an extension of a recursion principle called mathematical recursion, whereby if you're clever, you might be able to attack the infinities which are everywhere on the line. I think you know that. That's what Cantor was trying to solve. He, of course, couldn't, because it's literally impossible. It's either continuous or it's not. If you have a number system on the line, it's not continuous. Think about that, because that will lead you into the quantum paradox arena. Because that's essentially what we're trying to do, is we're trying to figure out why that's a problem when obviously it's a contradiction. So to get to the point here, always pardoning the pun, we have a circumference of 1. Is that true? Not exactly. We just said that yes, it is 1. You could say that and you would be right. No question at all. Yes, the circumference is 1. But did you say it right? Well, when you're saying 1, we are all taught in school that 1 is 1. 1 is 1 to the same proportion that 0 is 0. There's no second definition, man. Well, let's think about that for a second. Is this circumference 1? If you say it is, and you can prove it is, then you can assume it is. That's called the scientific method. We just did so on that, but it does use an irrational. Irrational. What does that mean? Search your memory banks. We're not going to go into that now, because it actually is a very interesting thing to answer. What does that mean when you say irrational? You might guess right at the outset, if you didn't know, or if you did know, you're just rehearsing what you do know, that it is not, that is negative, not rational. What is rationality? It's the ability to compose a number as a fraction. That's the exact definition. It's the ability to compose a number as a specific relationship between two numbers. Now, in geometry, according to the Greeks, those numbers have to be quantities. But pi is not quite a quantity. This is what Cantor and everybody else argued against. No, it has to be a quantity because it's on the line. Is that true? John Horton Conway proved conclusively that although all the irrational numbers we've ever met are all on the line with the rational numbers, the irrational numbers literally outnumber the rational numbers by several orders of magnitude, depending on how you count magnitude with abstract quantities, which is transcendental logic, which apparently John was able to master because he was able to draw a number tree that all the analysts who were able to analyze it, and John is and was one of the most famous mathematicians of all time, he said in his tree diagram, the tree diagram is what said it, he defined all the numbers on the line with a binary descent progression. In other words, a tree structure. I'm a database manager by trade, so this makes sense to me. I don't want to overwhelm you with strange concepts and terms. But I do want you to know that John defined what is a linear number, and it definitely includes the irrational numbers. So the irrational numbers, including pi, including our magic number 2 pi, even though it's irrational, it is a linear number and can be treated to linear mathematics. It's just that you'll never have it absolutely precise. You may guess that's where the calculus comes in. You would be absolutely right, and in my class, you would get an automatic A plus for the semester, and you're going to go on to wherever you want to go from my class. Because once you see that, you have seen much more than your mathematicians are willing to face. And it shows. And it's sad, because the mistake of using irrational numbers is absolutely fatal. And the Greeks knew that. It practically destroyed the Pythagoreans in some way, although that may be a legend. It's a credible legend, because they discovered that irrational numbers do exist, and they were crushed. They knew what that meant. It meant that they would never be able to geometricize the circle. Not in the way that Euclid was able to geometricize the line. The line we know. Why is the line so familiar to us? The physiologists, as I began to say, were able to prove. And this was after a long debate, because the evidence was not conclusive until a certain threshold, and then it was realized, you know what we've discovered in physiology? That is, a branch of biology. How do we see? What do we see? If you've ever been to a movie, or just looking at your cell phone, or presently, which is probably the best example, looking at my face on the screen, does it look like I'm there? Yes. So, are you seeing me? No. You're seeing a flat image. It's flat. So that's how we see. That may seem obvious once it's explained, but that took a long time to prove, because we also see depth. And a flat screen does not have depth. It's flat. You're imagining you see depth. Imagining is kind of a stretch. No, we're not imagining that we see depth. It's that we're using a slightly different process than just seeing the flat screen image. We can't tell the difference between reality and a flat screen. That's why it's such a profound discovery, because it confirms what we already know from experience, that we cannot tell the difference between a well-produced movie and reality. We cannot tell the difference. There are subtleties at the edges of perception, though. And under some circumstances, you can convince yourself and maintain the conviction one way or the other. That when you're looking into the night sky, you may think, gosh, that looks just like a flat screen image. But I don't think you're going to talk yourself into it. But that is what you see. When you see the moon, do you see a sphere? You may want to hesitate before you answer. I would, because you see it in two ways. But you see, the moon is not moving in that frame of reference. Of course, it actually is. But you can't see it moving. When you look at it, you see a snapshot. Because it doesn't look like it's moving. It's too far away and it's moving too slowly. So it looks like it's just sitting there. Oh, that old moon just hanging in the sky like a big Mississippi boat or something like that. But it is a circle, not a sphere, that you see. Well, you see a circle here. Could you say that you're seeing a sphere? Oh, yes, of course you could. See, that's actually rather profound because that's a second transformation. The transformation, it's called an equation can be called a transformation in another context. What we want from the radius is the circumference. Oh my goodness, nothing could be easier. All you have to do is use that irrational constant. Is that a contradiction? In one context, it is. You'll see that because it leads directly to the quantum paradox. The quantum paradox is best described as a mathematical error. Our mathematics has been unable to penetrate this paradox, so mathematics has failed, QED. So what went wrong with our mathematics? I think you're starting to see that you might be starting to see the problem itself. You are. This leads directly to a direct perception of the collapse of the wave function. And you're looking at it. So what is that circle that makes it so special? When I say that it's the invert unit circle, because the unit is no longer on the radius, the unit has been transferred to the circumference. Can you do that? Of course you can. You can see it and use the equations to prove that that circle is a perfect one. What's wrong with saying that? What is wrong with saying that? There's something vastly wrong with saying that, even though we just proved it's true. It's really difficult to answer that question, and I'm just teasing you because now I'm going to tell you the answer, but I hope it surprises you. The reason why you can't just say, in the same way that you say, that the radius is 1, by inverting the equation and getting the circumference equal to 1, which is precise, there's no error there. But then what you say is, you say that the circumference is equal to 1. That is a mistake in nomenclature because you're using the word 1 as if it meant exactly the same thing as the radial 1, often called a radian, so that the true distance around the circumference is measured in radians, which is a curved number, if you think about it. And what is that radian? 3? It's more than 3 radians around. So it's more than 3 radii. It's just a fraction more, as it would have to be, otherwise it would be 4 radians or more. Is it precise? If we say it is, well then something has to be imprecise. Because the relationship between those two quantities is the relationship between a rational quantity and an irrational quantity. And on the unit circle, you've decided that the radius has to be rational, which makes rational sense. But then you're stuck with an irrational number, and then whatever you do with it, you simply have to make a footnote. It is irrational. It is not rational. That turns out to be a fatal difference, and I'll show you why. But first, let's just capitalize on what we actually know. Is that circumference 1 when the radius is the inverse of 2 pi? Can that be said? No. Not if you want to be accurate. It's not 1. Why not? It's because it's not the same one. Why not? We just proved that it is. Yes, but you took an extra step that they taught us in school you can just do without thinking, which is called the reduction of the fraction. That's a separate step. The actual result is 2 numbers, correct? Think about it. What is the correct answer? You have to say 2 numbers. With the radius, you only say 1 number. You say 1 and that's correct, because it's a linear number. On the circumference that we compute from an irrational radius, we get a rational circle number. The circumference is a rational circle number now, but now it's explicitly rational. And it is rational. 1 is rational, we say, because it could be written as 1 proportion 1. Is the inverse true? No, the inverse is not true. And that's what I discovered. That is a huge. It should be, if you haven't figured this out, if you're not saying, wow, yes, yes, I see it, I know it now, I can teach it, it's true, you proved it. If you're not saying that, and you might not be, this is a monumental blunder on my part. I'm making an incredible error by suggesting this. Because all mathematics and all mathematicians agree, so far, that 1 over 1 is equal to 1. And you could prove that that's true. But you can only prove that it's true mathematically. Now, you could argue with that, and you should, because you might want to argue that because it's actually, this is the definition of a superpositional answer. This is incredibly profound, so I hope you hang on here. The definition of a superpositionality in this context, which has a wide range of contexts, is that it's not exactly binary. There's a conjugal relationship which is not binary, which is plus minus. Instead, it's conjugality, which is this ortho relationship on a perpendicularity, we call it. You can see the perpendicularity here. Well, we solved that by integrating the two perpendicular segments. So you could say that the vertical radius is whatever it is, and the horizontal radius is whatever it is, and you can conjugate those. Well, that's what we just did. So we do have two ones. It's 1 over 1. The only right answer is 1 over 1, unless you say it correctly, because when you say 1 over 1, you're not saying it in the best way you could. And it is significant. You're saying it's 1 divided by 1. That is incorrect, because that's the linear interpretation of the inverse of multiplication. And multiplication is not a linear operator. And neither is division. What kind of operators are they? I'm going to show you that they're circular operators that behave the same way in their space according to their operator, which is the paired operator multiply and divide. It's not add and subtract. It's not polaric. It's conjugal, which is orthogonal. So they're two orthogonal numbers. And those ones are at right angles. And I'll show that to you. You can actually see it if you're clever. But the fact that that circle is a two-component 1 puts it in a different space than the radius. And so what is being proved here is that the linear grid is not in the same number space as the circular grid, which is called a polar grid, which you compose by, instead of drawing two straight lines, you draw a tiny circle, and you do the same thing as you do with a line, and you say that the first jump is from 0 to 1, but it's to make the circle. So whatever you do to get a circle out of a point, it's the same thing as getting a line segment out of a point. Think about that. This is quite deep. But when you switch to circular space, you don't make the quantum jump from 0 to 1. You make the quantum jump from 0 to 1 proportion 1. Can I prove that? Let's do it now. We have just made that circle, so let's use it to see if we can prove anything with it. Let's see if we can prove my statement that that's a reparameterization of the number space of the plane, so that you're no longer using add at all. That's a major step forward in the evolution of man's mind and science progress. It changes everything. I just changed 2,500 years of history. We've been using the derivative space, which requires x and y conjugated on x squared plus y squared equals the hypotenuse squared, which that's all been done. You know that. But that's how you get at the space in linear 2D space, is with the Pythagorean theorem, and there's no other way to do it. And that can be proved. It hasn't been proved, But is there another way to do it? Yes, but it's taken 2,500 years to see the other way to do it. You can abandon addition and just rely on multiplication. Can that be done? Yes, we're going to do it now. So when you begin with a point, Euclid did too, so we're certainly warranted in beginning our definition of a new space for the plane. The plane is an undefined space because it has no edge. And what you're trying to do is get numbers into the plane, whether it has an edge or not. Just put numbers into it so you can start to talk about what's in the plane. Well, if you do that in 2D, you're stuck with linear algebra. But I discovered you don't have to do that because you don't have to rely on add to parameterize the space with numbers. But in order to parameterize the plane with numbers, you can't use linear numbers. But you have to use linear numbers to compose the new number space. That's magic. And that's what I discovered. And that's 40 minutes. And in the next lecture, we'll get much closer to the collapse of the wave function. But now, I think you may be able to guess how you're going to be prepared much better now to see the quantum jump. If you don't see that, it just seems like I'm adding to the mystery. Actually, I'm not adding to the mystery. I'm subtracting from the mystery step by step until we get to where the mystery begins. But we have to do it in my space because it's the only space that can show you geometrically the collapse of the wave function. All right, thank you very much for tuning in. I'm very excited. I actually have goose flesh, as my Ukrainian wife would say. We here in English-speaking America would say goosebumps. But you're going to see this, and I hope I'm able to do this in the next video lecture, which may be later today. Thank you again for tuning in. It means a lot to science. It means a lot to you and me. I hope it means a lot to you because you're involved now. You're going to get this, and you're going to be the first. And you're going to reap the benefits I already have, but you don't know I have any benefits at all. You won't need to wonder pretty soon. Thank you. Keep looking up. We're just nearing the end of the new moon cycle. I never did give my reading from the Quran. That is, I didn't make a video, but I did read from the Quran and was able to complete my study on Surah 6, the 6th of 114 surahs, in one of the most holy transmissions ever given from heaven to earth through Muhammad at the behest of the Most High, blessed be his name, when he assigned Gabriel, one of his 4 most holy angels, to talk to Muhammad out in the Arabian desert about 1,400 years ago. We'll be right back.